Carbonyls are coordination compounds of transition metals with carbon monoxide. Depending on the number of metal atoms, carbonyls are divided into two types: monomeric or mononuclear carbonyls and polynuclear carbonyls. Mononuclear carbonyls contain one metal atom per molecule. For example, tetracarbonyl nickel 0, pentacarbonyl iron 0, hexacarbonyl chromium 0 and hexacarbonyl tungsten 0. On the other hand, polynuclear carbonyls contain two or more than two metal atoms per molecule. For example, decacarbonyl dimanganese 0, octacarbonyl dicobalt 0, octacarbonyl dirhodium 0 and decacarbonyl dirhenium 0. It is important to note that in carbonyls, the electrons that form the chemical bond between the metal and the carbon of carbon monoxide are supplied solely by the molecules of CO. Hence, the metal atom is said to be in zero oxidation state. In a metal carbonyl, the metal-carbon bond has sigma as well as pi character. A sigma bond between a metal and a carbon is formed by the donation of a lone pair of electrons on the carbon of the CO molecule to a vacant orbital of the metal. A second bond is formed by back bonding. This bond is a metal-to-carbon pi bond formed by the sideways overlap of a full dxy orbital of the metal, with the empty antibonding pi star 2py orbital of the carbon of the CO molecule. This bonding creates a synergic effect that strengthens the bond between the CO molecule and the metal. The total bonding is, thus, M double bond C double bond O. Carbonyls have simple and well-defined structures. For example, tetracarbonyl nickel 0 is a tetrahedral molecule. Pentacarbonyl iron 0 is trigonal bipyramidal. And hexacarbonyl chromium 0 is octahedral. Decacarbonyl dimanganese 0 is made up of two square pyramidal units joined by an Mn-Mn bond. The molecule, octacarbonyl dicobalt 0, consists of two trigonal bipyramids with one edge in common. Let's now study the stability of coordination complexes. The stability of a complex in a solution refers to the degree of association between the metal ion and the ligands involved in the state of equilibrium. Transition metal complex ions differ considerably in their stability. Their relative stability can be expressed in terms of an equilibrium constant called the stability constant. The reaction between the metal ion and the ligand may be represented as M plus Nl in equilibrium with MLN, where N represents the coordination number of the metal ion, M for the ligand L. Note that the charges are omitted for the sake of generality. Now, applying the law of mass action to this equilibrium, we get K is equal to concentration of mLn divided by concentration of M multiplied by L raised to the power n. Here, K is known as the formation equilibrium constant or the stability constant of the complex. The numerical value of the stability constant is a measure of the stability of the complex in solution. The greater the value of the stability constant, the more stable is the complex. The reciprocal of the formation constant is known as the instability constant or the dissociation constant. It is important to note that as free metal ions rarely exist in a solution, complex formation reactions are usually studied in solutions. Metal ions are usually surrounded by solvent molecules that will compete with the ligand molecules and be successively replaced by them. Consider the reaction MH2ON plus NL in equilibrium with mLn plus NH2O. The stability constant for this equation can be written as K is equal to concentration of mLn divided by concentration of MH2ON multiplied by L raised to the power of n. Note that the molar concentration of water is ignored because its concentration remains almost constant. This reaction is assumed to take place in several steps with suitable formation constants in each step. The first step may be written as MH2ON plus L in equilibrium with MlH2ON minus 1 plus H2O. Stability constant K1 for this step is equal to concentration of MlH2ON minus 1 divided by concentration of MH2ON multiplied by concentration of L. The second step may be written as MlH2ON minus 1 plus L in equilibrium with Ml2H2ON minus 2 plus H2O. Stability constant K2 for this step is equal to concentration of Ml2H2ON minus 2 divided by concentration of MlH2ON minus 1 multiplied by concentration of L. Similarly, for the nth step, the reaction can be written as mLn minus 1 H2O plus L in equilibrium with mLn plus H2O. The stability constant for this step can be written as Kn is equal to concentration of mLn divided by concentration of mLn minus 1 H2O multiplied by concentration of L. Here, the stability constants K1, K2 and Kn are referred to as stepwise stability constants. Alternatively, the formation of a complex may be due to the simultaneous addition of ligands to the metal ion. How do you, then, express the equilibrium relations? When only one ligand is added to the metal ion, the equation may be written as M plus L in equilibrium with Ml. The expression for the stability constant for this equation may be written as K1 is equal to concentration of Ml divided by the product of the concentrations of M and L. If two ligands are added to the metal ion, then the expression may be written as M plus 2L in equilibrium with Ml2. The stability constant for this reaction, K2, is equal to concentration of Ml2 divided by concentration of M multiplied by concentration of L raised to the power of 2. Similarly, if N ligands are added to the metal ion, then the equation may be written as M plus NL in equilibrium with MLN. And the stability constant for this reaction, Kn, is equal to concentration of MLN divided by concentration of M multiplied by concentration of L raised to the power of N. The stability constants K1, K2 and Kn are known as overall stability constants or overall formation constants. The stepwise and overall stability constants are, therefore, related as beta n is equal to the product of K1, K2, K3, and so on up to Kn. Stability constants tend to be very large numbers. To simplify the numbers, a log scale is often used. Thus, the relation between the stepwise stability constants and the overall stability constant can be written in log scale as log beta n is equal to log K1 plus log K2 plus and so on up to log Kn. Consider the formation of the complex tetraamine copper 2 to understand this better. The addition of ammonia ligand to cupric ion may be considered the first step. The stability constant for this step may be written as K1 is equal to concentration of CuNH3 2+ divided by the product of the concentrations of Cu2+ and NH3. The experimentally determined value of the stability constant for this step is 1.78 multiplied by 10 raised to the power of 4. When quoted in log scale, its value is 4.25. The second step can be written as CuNH3 2+ plus NH3 in equilibrium with CuNH3 2+. The stability constant for this step may be written as concentration of CuNH3 2+ divided by the product of the concentrations of CuNH3 2+ and NH3. Its value is log 3.61. The other two steps of the addition of ammonia ligands and their stepwise stability constants are as shown. The overall stability constant is simply the equilibrium constant for the complete reaction. Cu2 plus 4NH3 in equilibrium with CuNH3 2+. It is given by the expression beta 4 is equal to concentration of CuNH3 2+ divided by concentration of Cu2+ multiplied by concentration of NH3 raised to the power of 4. Its value is 1.20 multiplied by 10 raised to the power of 13. In terms of log scale, it is equal to 13.28. Thus, it can be seen that the sum of the logs of the stepwise stability constants is equal to the log of the overall stability constant.